Hello, welcome again. We are solving some conventional questions of machine design. The topic is coupling. Question number 7 from Engineering Services 2013 is a 100 steel drive shaft transmitting 150 kilowatt at 300 rpm has to be connected to a machine having same diameter shaft with a cast iron CI unprotected plant coupling. The permissible shear stress for the shaft, bolt and key are 50 MPa. The bearing stress for bolt and key are 50 MPa and shear stress for CI is 8 MPa. The basic dimensions of coupling may be assumed as per the standard. Design the coupling and verify all major dimensions for strength. So here this is your unprotected flange coupling. This is your unprotected flange coupling. This is your shaft and diameter D. This is your hub, okay, and its diameter is 2D according to standard. And these are the bolts, and here the circle diameter is 3D. Small d is diameter of shaft. Okay, and this is your key. That is 1. Its length is approximately equal to length of hub. So that is equal to 1.5 d. Okay, and this is your the diameter of bolt is d1. Okay, so now power is given, that is 150 kilowatt, so that is 150 into 3 watt, and diameter of shaft is given, that is 100 mm. RPM is given 300 RPM, and these stresses tau, shear stress in shaft, bolt and key are given, that is 50 MPa, and shear stress in and bearing stress in key and bolt is also given, that is 50 MPa, and shear stress of the cast iron is given, that is 8 MPa. So first of all we will design shaft. To design shaft we will calculate torque transmitted from power and RPM. As power is given as 150 kilowatt, so RPM is given as 300 RPM. So using 2 by nt by 60 is equal to P, we can find out torque. So torque comes as 4774 Newton meter or 4774 10 to the power 3 Newton mm. Okay. So now to find out the, first of all we design shaft. Okay. So to find out the diameter of shaft we will use that torque. Okay, and we'll take that shear stress and use torsion equation. According to torsion equation, P is equal to pi by 16 tau s d cube, and d cube comes out as, because T is known, tau s is 50 MPa. Okay, so D comes out as 78.64 mm. So but diameter given is here 100 mm, so which is within the safe limit. So that is the design of shaft. Okay, so now we'll design hub. So according to standard, the outer diameter of hub is just 2d, that is if d is 100, then outer diameter of hub is 200 mm. Okay, so now this hub is like a hollow shaft. This hub is like a hollow shaft with outer diameter 2d and inner diameter of shaft. Okay, and this is made of cast iron. So again we use torsion equation and find out, we check this, find out the shear stress involved in it. So according to torsion equation, the torque in hollow shaft is pi by 16 into tau c d4 minus small d4 divided by d. Okay, so now capital D is your 200 and small d 100. So from this we can find out tau c comes out 3.24 MPa. So as the permissible shear stress for cast iron is 8 MPa, so it is within the safe limit, so it is okay. Okay, next step is to design key. So key is almost of equal length of hub, and length of hub is 1.5 d, so length of the key is 1.5 d, and we and equal to 150 mm. And we assume that now we assume that key is your square key, and square key T is equal to W is equal to D by 4. So D is your 100 mm, so thickness of key is your 25 mm, and the width of key is your 25 mm. Now we'll check it in shear and crushing. So so this is your key. Okay, So shearing will take place along this plane, perpendicular to this. Okay. So perpendicular to this, there will be width and there will be length. So L into W, L into W is your shearing area. L into W is your shearing area. Okay. And if you multiply by shear stress, then it will be force, and this force is at a radius d by 2 or at the periphery of shaft. Okay. So now this force multiplied by d by 2 will be equal to torque. Now we can put the value of L, W, T and small d and find out tau k. So tau k comes out as 25.46 MPa. So which is also safe because permissible shear stress for key is given as 50 MPa. Okay. Now we'll check it for key for crushing. For crushing, the area as this key is getting crushed between hub and shaft, so in this portion. So area for this portion is L into, because this is your T, so L into half in shaft and half in hub. So it will be T by 2. This will be T by 2 and this is L. So area for crushing is L into T by 2. And if we multiply by bearing stress, then we are shearing bearing or crushing force, and if it is multiplied by d by 2, then it is torque. So now we'll check for sigma bk, because we have all the values L, T, D and capital T. So sigma bk comes out 50.92. So that is not safe, because bearing stress for key material is given as 50 MPa. So we'll redesign the key. Okay. So if according to stress as 50 MPa. Now we'll find out T. So T 25.46. So for safety we'll take as 26 mm. Okay. So this is your 26 mm. So next step is to design to flange. So flange thickness is, this is your flange. This is your flange. This is your flange. Okay. So flange can fail here, okay, or here. Okay. And area responsible for failure is circumference of hub, okay, and thickness of flange. Okay. Thickness of flange is this, and circumference is pi d, pi capital D, or 2 pi d if we take small d. Okay. So it is circumference of hub into thickness of flange. Okay. So this is your area responsible for failure, and if we multiply by shear stress, okay, then it will be force, and as it is acting at outer periphery of hub, so it is multiplied by d by 2 to get torque. So now we'll put these values. So circumference of hub is pi d and this is Tf, and now we can check for crushing stress, shear stress. So shear stress comes out at 1.5 MPa. So which is also safe because it is also made of cast iron, and cast iron permissible stress is 8 MPa, so this is safe. Now we'll design bolts. So load, because the bolt will also try to fail along this. One part of flange will go here and another can stay here, so bolt can fail here. So area responsible for failure of bolt is pi by 4 d square, d1 square. d1 is diameter of bolt. Okay. d1 is diameter of bolt, and if we multiply by shear stress, then it is load on the bolt, and if we multiply by n number of bolts, then it will be total load on bolt. And if we multiply by d1 by 2, that is radius of the pitch circle radius of the bolt, that is 3d. So then we can find out d1 is what Kelvin, and we can check it for crushing also. For crushing it will be n into d1 into tf into sigma b d1 by 2, so that is 17.68, that is within safe limit.